Hey guys, so today I want to tell you a little bit about the research that I have been doing at INL together with my supervisor, Professor Ernesto Galvão. So this is research in the area of quantum computation, and in particular we have been working on circuit compilation and hybrid computation. The motivation behind this work is that current quantum hardware is still limited in its capabilities, and so what we would like to do is to develop smart schemes where we can combine a classical computer with one of these small quantum chips in order to try and achieve quantum advantage in the near term. And to that end, this Pauli-based model of quantum computation seems very promising, because within this model, this quantum classical hybridization sort of arises naturally. So how does this model work? Well, in this model, the computation is driven by a sequence of adaptive and non-destructive measurements of Pauli operators. What does this mean? Well, adaptive means that we don't know what the second measurement is until we have the outcome of the first. We don't know what the third measurement is until we have the outcomes of the first two measurements, and so on. And non-destructive simply means that the qubits need to survive each of these measurements so that they keep on being measured along the sequence. So what was our contribution? Well, what we did is we proposed a new way of actually implementing these multi-qubit Pauli measurements, and our proposal is asymptotically better than previously existing proposals in literature. Secondly, we actually wrote code that compiles quantum circuits using this model of quantum computation. And so here I'm just going to give you a very brief overview of some of our results. So we have some original circuits, which here we depict as green crosses. And first we just sort of precompile them with a tool that is already existing in literature. And with that we get the orange crosses, which, as you see, involve a lower number of layers, which is good. And then we used our own tool and got the blue dots, and you see that these circuits are significantly shallower than the original ones, which is great because it's the kind of result that we want to have. And we did this for several different features of the circuit. So for instance, here you see a similar graph, but for the single qubit gate count. And again, you see that the original circuits have a very large number of gates, but by comparison, our compiled circuits have a very few number of gates. And finally, Pauli-based computation also allows you to easily simulate a certain number of virtual qubits. What do I mean by this? Well, suppose that you have a quantum computation that you want to make and that you require n plus k qubits. But your quantum chip is small, and so you only have access to n qubits. While in Pauli-based computation, you can still do this computation, and you do it by simulating the extra k qubits in a classical computer that you have access to. So you're actually doing a bigger computation than the quantum chip alone would allow you. So I hope you like this brief flavor of the research that we have been doing. If you're interested in this kind of stuff, please check out arXiv or feel free to contact me in any way. And thank you for your attention.